Greetings. This is Christopher LaForge coming to you from the South Shore of the Lake Superior watershed, and today I'm happy to make a complimentary lecture called Battery Capacity, the Basis of Storage. My background includes being a certified photovoltaic installation professional certified by NABCEP, the North American Board of Certified Energy Practitioners, and also being an IREC certified master trainer under the PV installation professional type. IREC, of course, is the Interstate Renewable Energy Council. This presentation is recorded and copyrighted for 2014. So we will begin with nomenclature. What do we mean and why does it matter? A few terms are essential to move forward with this topic, and so we're going to run through them quickly. This may be quite a bit of review for most of you, but we want to be on the same basis where we start, so we'll start with some basic terms. Amp, for instance, is short for ampere. An ampere is, of course, a measure of the flow rate of electrical charge. It's equal to 6.241 times 10 to the 18th charge carriers, also known as electrons. This is also equal to 1 coulomb. This is in relative terms based on its relation to time as well. So that is 6.241 times 10 to the 18th charge carriers or electrons per second. The term amp is important for understanding electrical capacity issues, as are most of the terms I'm going to go over here. Amps, just for shorthand, remember, is the measure of the flow of the electron charge. The next term is volt. Volts are the derived units of electrical potential. They are electrical potential differences, voltage, and electromagnetic force, which is defined as the difference in electrical potential between 2 points of a wire when an electric current of 1 ampere dissipates 1 watt of power between those points. That is equal to 1 volt. Again, this is important for understanding our capacity issues. And finally, for this slide, wattage, we start with a watt, which is the derived unit of power used to express the rate of energy conversion or transfer with respect to time as well. A watt is the rate at which work is done when 1 ampere of current flows through an electrical potential difference of 1 volt. This becomes the ground of understanding our relationship between power, which is represented by wattage, and electromotive force, voltage, and current flow, which is amperage. And as we all know, watts are equal to volts times amps. To continue, we want to discuss capacity, and so we're going to have to be able to look at the amount of charge available for a period of time. This leads to terms which are commonly used, including amp hour, which is a unit of electrical charge equal to the charge transferred by a steady current of 1 ampere flowing for 1 hour. That's 1 amp hour, which is also equal to 3,600 coulombs. A milliamp hour is 1/1000th of an ampere hour, and we will see that this is our basic metric for battery storage from manufacturers. Milliamp hours are used with small portable batteries, and amp hours are used with larger batteries. Watt hours represent a unit of energy equivalent to 1 watt of power expended for 1 hour. Watt hours give us a metric that allows us to understand what power is required for providing our typical appliances, which are often measured in wattages. Next is the C rate. C rate we will get into quite a bit, is the measure of the rate at which a battery is discharged or charged. A 1C rate is defined as the discharge current divided by the current draw under which the battery would last for 1 hour. A 1C discharge rate means the battery will be completely discharged in 1 hour. And this unit greatly affects how we understand battery capacity, and it adds some very nice complexity. Finally, the term cycle is referring to a charge or discharge cycle, and it is the process of charging and discharging a battery. The term is used when specifying battery's expected life, as in the number of charge cycles a given battery will be expected to provide. And of course, cycling batteries is what battery capacity is all about. Storage is based on what common elements are used to make up the battery. Batteries have very basic construction, and they are made up of cells. Batteries consist of one or more electrochemical cells that are capable of changing stored chemical energy into electrical energy. The battery cell contains both a positive terminal, which is called the cathode, and a negative terminal, which is called an anode. And between them are electrolytes, which are chemical mediums that allow the flow of electrical charge between the positive cathode and the negative anode. Here is a small representation of a common lead-acid battery cell. Many lead-acid batteries are made of lead oxide as the positive plate and lead as the negative plate, with a hydrogen sulfate electrolyte. Batteries are broken into two major categories. First are the primary batteries, which are your small non-rechargeable battery cells, your A's, AA's, AAA's, C's, D's, 9-volt cells that are not rechargeable. For our discussion, we won't be spending much time on primary cells at all. We're going to be talking about secondary cells because we're into battery capacity and storage for long-term applications in photovoltaic systems. Secondary cells are the rechargeable cells. Now, there are far too many to list briefly, and for PV systems, we're really only using secondary cells. So we want to be considering deep cycle batteries, and for the most part, this discussion will surround deep cycle lead-acid batteries. Additional deep cycle secondary cells include nickel cadmium, nickel metal hydride, nickel zinc, silver oxide, and lithium ion. Now, the nominal cell voltage for a lead-acid battery is 2 volts. That's why when you look at your automotive starting battery, there are 6 cells in it, and that makes a 12-volt battery. With the other more exotic battery types, your combination of cells will vary based on the nominal cell voltage. So we see nickel cadmium has 1.2 as its nominal cell voltage. Nickel metal hydride also 1.2, roughly speaking. Nickel zinc is a higher 1.6 volt. Silver oxide is also 1.6 volts. And lithium ion comes in 2 primary categories. There's actually many more, but the main 2 are a 3.2 volt cell, which is a lithium iron phosphate positive with a graphite negative, or a 3.7 volt cell with a lithium nickel manganese cobalt, also known as NMC oxides for the positives with graphite negatives. For our discussion, we're going to focus on lead acid batteries for several reasons. We do this because, first of all, lead acid batteries currently offer some of the best cost per amp hour ratio over the cycle life of the batteries. This is in fact changing, and we are going to see that certain batteries will compete and are actually starting to compete with lead acid batteries, most notably the lithium ion batteries that have begun to be developed for automotive applications. Currently, lead acid batteries are still the best cost per cycle life per amp hour, and so that's why we'll focus our discussion there. They're the most widely used in our static PV storage applications, and the discussion of battery capacity will actually apply to all the various types in a very similar fashion. So if you're wildly excited about the advent of lithium ion or other battery types such as nickel metal hydride, it's going to apply in a very similar fashion how we discuss battery capacity. So don't worry, it'll all apply. Basically, the capacity of any battery is created by the combination and type of the active materials in the battery. That means that the size of the surface area of the plates, the plate density, and the makeup, and the quality of its electrolyte and its quantity are all going to influence on how much capacity a battery will give you. In deep cycle lead acid batteries, you see lead plates and lead oxide plates that have a much higher density than in automotive starting batteries. And the reason for that is that automotive starting batteries use a spongy form of lead that provides greater contact with the sulfuric acid electrolyte, allowing the battery to put out a great deal of amperage all at once to start your cranking motor. But it has a decent lifespan because it is immediately recharged. For our static photovoltaic and other renewable energy battery storage applications, we want a battery that can be discharged over a long period of time at a less dramatic rate and hold that charge for a long period of time. So the plates are more dense and they are larger and there's more of them. So in our typical lead acid battery, they're all going to have the same basic components. You're going to have a positive plate and a negative plate, a cathode and an anode, and you're going to have some sort of plate separators and a case for the containment of the electrolyte and your sulfuric acid electrolyte solution. Now, capacity in a battery is derived at manufacturers by discharging the battery, and this discharge is done at a constant amperage until it goes below its useful voltage. This is referred to as the terminal voltage. Standard test conditions do this at a constant temperature as well, usually 25 degrees Celsius or about 77 degrees Fahrenheit. The battery's capacity then is calculated by multiplying the discharge amperage by the time it took to reach that terminal voltage. So 1 ampere hour is going to represent the unit of electrical charge transferred by the current of 1 ampere for 1 hour. In our static storage systems, we most often use a cumulative amp hour meter, not unlike the one represented here. Cumulative amp hour meters come in many varieties, but the best ones not only use shunts to measure the current flow into and out of the battery, calculating the amp hours, but they also calculate the aging of the battery and adjust the Peukert's constant, which we will learn about, to adapt and understand the actual capacity remaining in a battery as the battery ages. Amp hour meters are essential to understanding the actual on-site battery capacity of any given battery, because you are only going to really see what a battery is holding based on the battery's makeup, its amp hour capacity, and the amps put in and taken out of the battery. This can only be done with a very accurate amp hour meter, and attempts to measure capacity with other methods other than specific gravity are fraught with all sorts of problems. Of course, measuring specific gravity with a good hydrometer, is a good method of determining a battery's state of charge, but as we all know, having done it, it is messy and it requires you to introduce the hydrometer into each cell of the battery. This can lead to cell contamination, and as I just mentioned, it's quite a messy procedure. It is a good method, it is a good standard tool to keep in the toolbox, but for day-to-day measurements of capacity of a working battery, we use amp hour meters, and we try to make sure that they're advanced enough to give us the readings we need and to adjust for aging batteries by adjusting the Peukert's constant. So there are many parameters that affect the measurement of a battery's capacity. In the testing process, we've got at least 5 that we have to take into consideration to understand how battery capacity is presented. We will go over these 5, which include the C rate, the battery temperature, battery age, Peukert's constant, and cycle depth. First, the C rate. As we pointed out in our nomenclature, the C rate refers to the charge rate. And it was defined in the 1700s when Charles Augustin de Coulomb proposed that a battery that receives a charge current of 1 ampere passes 1 coulomb of charge every second. So charge rate can be denoted as 1C, or a 1C rate, and it signifies a charge or discharge rate equal to the capacity of a battery in 1 hour. Most small portable batteries are rated at the 1C rate. So if we're talking about a 1000 milliamp hour battery, it will be expected to provide enough energy to achieve 1000 milliamp current for the period of 1 hour. This is how our small A, AA, AAA, C, D, and 9-volt cells are rated, all based on the capacity consumed in an hour. We will see that there are many different C rates to consider, and we need to be able to understand them. We will talk about them more as we move on. The second parameter I'd like to discuss is temperature. Now, as I pointed out earlier, batteries are generally tested and specified on the assumption of an operational temperature of 25 degrees Celsius or about 77 degrees Fahrenheit. So as we move out of that range, the battery performance changes. At a slightly higher temperature, batteries may perform a bit better, but they will be aged more quickly, and at high temperatures, batteries will be significantly damaged. We do not want to be operating batteries in excess of 100 degrees Fahrenheit. At the same time, batteries, as they go below the standard test procedure at 25 degrees Celsius or 77 degrees Fahrenheit, we see that they reduce their capacity. Now, this is an apparent reduction in capacity. The battery's capacity is still the same, but as we get below 77 degrees, the battery capacity is not available. And when we get below 32 degrees Fahrenheit, we'll see that there is significantly lower capacity. And the battery really hasn't lost its energy, but because the cold temperature restrains the chemical activity of the battery, the accessibility or availability of the capacity is reduced. Here we have a chart indicating how much, as batteries go below the standard test condition temperature, how much its available capacity is reduced. And we see that as you get to, say, 10 or 20 below Fahrenheit, we've really lost as much as half of the battery capacity. Now remember, as the battery becomes discharged, if we put it in a cold environment, the electrolyte is no longer highly acid and it can easily freeze. Freezing batteries will destroy battery cells and end their lives quite prematurely. So we want to make sure we keep our batteries charged. We want to keep them in a good temperature, and if they're going to get cold, we do not want to discharge them greatly. The third parameter we're going to touch on now is age. As batteries age, there's a depletion of the battery's active material and also sulfation that builds up on the plates in lead-acid batteries. Now, both actions reduce the conductivity of the plates and therefore the battery's capacity. Careful maintenance, including regular equalizing charges, will slow battery aging, but all the batteries are going to eventually age and become useless. Now, how aging affects the capacity of a battery depends on how the battery is operated. So we have a small chart here indicating that if we regularly discharge the battery to 100% DOD, which refers to depth of discharge, we're going to get far fewer cycles than if we only discharge to a 50% depth of discharge or a 30% depth of discharge. This greatly affects how we want to run our batteries. In my system design for static applications of photovoltaic systems, I generally plan to not be discharging the battery more than 50%. I truly like to cycle the battery in the top 25% of the battery's capacity. This is going to obviously give me a great deal of extra battery life. We can see in this chart, just roughly speaking, for this company's battery, we're looking at getting upwards of 1,200 cycles at a 30% depth of discharge versus roughly 500, 450, 500 cycles if we're going to 50%, and only about 180 cycles if we go to 100% depth of discharge. The critical fact here is that the amount of energy that a battery is going to provide is influenced by both the rate at which the power is removed and the depth to which it is discharged. If we take the power out of the battery in large quantities in high amperage rates, the capacity available in the battery is reduced. If the power is removed more slowly, the capacity is increased. So manufacturers provide battery capacity data at different discharge rates based on the amount of time the capacity is consumed by that given rate. So the capacity of a given battery can be represented by its 6-hour rate. In terms of the 1C rate, this would be a 0.166 C rate. Another common rate is the 20-hour rate. And in compared to a 1C rate, that is a 0.05 C rate. And there's also the idea that you might discharge a battery over a 100-hour period, and that would be the 100-hour rate, which is equivalent to 0.01 C in comparison to the small battery 1C rate. So Puchert's law is going to show us that the capacity of the battery is based in part on the rate that it's discharged. As the discharge rate increases, the battery's available capacity decreases. So here is Puchert's law. Now this was the great German scientist W. Puchert, and he mathematically represented the fact that the battery's capacity changes based on the rate at which it is discharged. His law can be expressed as IT equals C times C over IH to the K-1. Now, what does that mean? What it means, we're just going to get into this lightly because Puchert's work is pretty in-depth, but what it means is that the IT is equal to the capacity in amp hours of a battery at a particular discharge rate of I. So in the equation, H here is the rated discharge time. I is the actual discharge current in amperes. C is the rated capacity at that discharge rate in ampere hours. K is the Puchert constant. T is the actual time to discharge the battery. Now, one thing that makes this all very interesting is that Puchert's constant is not a single constant, but rather it is based on the makeup of the components of the battery and its age. This constant, therefore, changes with each battery type and how old it is. Now, for lead-acid batteries, the value of K is typically between 1.1 and 1.6. And that constant increases with age, which will show that as the battery ages, its capacity decreases. And for our purposes, this is as far as we're going to go into Puchert's equation. But for those of you who are true battery nerds and are interested in the deep vagaries of Puchert laws, the equations that are representing it, and how you calculate changes in Puchert's constants, you can delve deeper into this in an article that was found at batterystuff.com, and here's the link. The people at Battery Stuff are true battery nerds, and they go in as deeply as you may ever want to go with this. But basically, what we want to understand is that the fact is the rate of amperage that we pull out of a battery is going to affect how much capacity that battery will yield us. And when we withdraw higher rates we're going to get less capacity from that battery. The fifth parameter I want to touch on is cycle depth. Now, aging of batteries is really not greatly a matter of months and years, but rather it's the number of cycles and the depth of each cycle. So if we cycle batteries in a shallow cycle, less than 50% DOD, depth of discharge, the number of cycles we're going to get out of that battery is increased, and the battery is effectively aging more slowly. Conversely, if each cycle is deep, 80% DOD or greater, the battery ages more quickly and its cycle life is reduced. As the battery ages, its available capacity declines. This is why in my photovoltaic system battery bank design, I am looking at the client's load profiles on a daily average basis, and then I'm designing the battery to not go below that 50% depth of discharge. In the full battery course, we'll see how I determine that and what it means to be not going below 50% depth of discharge, because I don't want to do that for extended periods of time, referred to as the autonomy period. And many of the battery designs we do allow for a 3 or 4 day period before we reach that 50% depth of discharge. This reduces the amount of backup charging we have to do on off-grid systems, and it also allows us for as good a battery life as possible. But you noticed in the previous chart that less depth of discharge, like a 30 or 25% depth of discharge, as I mentioned, will extend the battery life even further. So, although there is a limit to it, generally speaking, we don't want to be going below 50% depth of discharge. And if we can stay in a 20 or 30% depth of discharge cycle, we're going to get many, many more cycles out of the battery and a longer life. So here is one manufacturer's cycle life versus depth of discharge graph. We can see that our expected life cycles at 80% are roughly 10% of what a depth of discharge of only 10% would be. And if we compare a 50% depth of discharge, we're getting, roughly speaking, 1,000 cycles with this particular brand of battery. And at a 80% depth of discharge, we're only getting modestly more than 500. So you can see the value of moving to a lower depth of discharge in our cycle of the batteries. It's going to give us nice life. Here's another company's chart showing a similar sort of performance. We are very, very aware that in our process, during these cycles, the deeper we cycle, the more that the active parts of the battery degrade, the more our actual capacity is going to be reduced during the life of the battery. And the rough rule of thumb is going to be that we want to live in the top 50% of the battery's capacity in order to extend its life and not reduce its capacity dramatically. So as we said, the amp hour capacity of the battery is going to be based both on the rate it's being discharged and the amount of time it takes to discharge it. Now, battery manufacturers are usually using an 80% depth of discharge in their calculations of the battery's capacity for industrial usage. Many of the batteries we use in static PV system storage renewable energy system storage, are industrial deep cycle batteries that were developed for other purposes like traction batteries and fork trucks. And these batteries are expected to provide a great deal of power during the day and then be charged up rapidly overnight. So these industrial batteries are rated to an 80% depth of discharge. These large, for instance, fork truck type traction batteries will be rated at what we're calling the 6-hour rate. This indicates that it's going to be discharged by large ampere rates, and it will bring it to its terminal voltage in about 6 hours. Now this works in your typical industrial facility because the battery is going to be charged up, not unlike your automotive battery, overnight. They're going to use a large battery charger tied to the utility grid and charge the devil out of that battery, bringing its capacity back up to full, and the battery won't have time to degrade and sulfate as a battery that was sitting in a 80% state of discharge for an extended period of time. Now, in renewable energy systems, we are discharging more lightly because, in fact, we're going to be charging more lightly. Our renewable energy sources don't come in at 120 amps for 6 hours just to get that 720 amp hours back into the battery. Our sun comes up and it starts shining at a diffuse rate, with a small amount of amperage. It builds through the day to a higher amount of amperage, and then it declines. And so we're planning for more light cycling of our batteries, both on the discharge side, primarily because we're going to be light charging on the charge side. This leads us to usually employ a 20-hour rate, indicating the more modest discharge and charge rates. So the 20-hour rate is going to be the rate that brings the battery to its terminal voltage over 20 hours. Now again, for the sake of the rating from the manufacturer, they're going to be using a 80% depth of discharge or a 20% state of charge as the terminal voltage. The point here is that when we look at batteries on an industrial manufacturer's spreadsheet, we're going to see the 6-hour rate very regularly, and we may have to look more deeply to find the rate that applies to our use, which is more of the 20-hour rate. In renewable energy systems, it's this light charging and light discharging that leads us to want to use the longer rate. So it's going to help to be able to convert the 20-hour rate to the 6-hour rate and back. If we're looking at a manufacturer's spec sheet and they're only giving us the 6-hour rate, we can convert the 6-hour rate to a 20-hour rate by multiplying it by 1.5764705. Now, in addition to that, if we're going to look at a 20-hour rate and we want to convert it to a 6-hour rate, we can just multiply the 20-hour rate by 0.84. This is a rough method, and it adjusts the rates adequately for our purposes. In the article that I wrote corresponding to this presentation, which is up on our HeatSpring website magazine, I've provided MK's, one of the battery manufacturer's handy little calculation converter tool, and you can find that at the end of the article on our site. It's just a nice little handy little conversion tool that'll show you the different rates and allow you to input data to convert one size from one to another. So we see these parameters are affecting the way that a battery is charged and discharged, how that capacity is presented, and how it changes. Remember, the C rate is referring to different discharge rates, and that affect our capacity over time. And our typical renewable energy storage rate is the C divided by 20, also known as the C20 rate. Temperature is going to affect our capacity as we operate the batteries, and lower temperatures are going to reduce our capacity. As batteries age, their capacity declines as well. We see that Professor Pucher gave us the idea that the rate of discharge is going to affect our available capacity, and he gave us the equations to work with that. And we now know that our cycle depth, our depth of discharge, is going to affect the cycle life and our battery's capacity. This set of issues is expanded on and illuminated in great detail in my 6-week intensive course, Batteries in Solar Photovoltaic Systems. Please send us feedback, comments, and your thoughts to me through the HeatSpring website. Thank you for your interest in batteries and their capacity. This is Christopher LaForge. You can find additional information at these helpful websites: Battery University, The Gizmologist's Lair, Electropedia, and BatteryStuff.com. This has been Battery Capacity, the Basis of Storage.